Okay, so welcome back to another video. So in today's video we have a limit. The limit as n approaches infinity of 1 divided by n times a plus 1 divided by n times a plus 1 plus 1 divided by n times a plus 2, so on and so forth, all the way up to 1 divided by n times b. So you can clearly see from the input that this is actually some sort of partial sum. And we'll be actually taking that as the limit as n approaches infinity. So in a sense, we're actually evaluating an infinite series. So I have nothing more to say, but let's actually just jump in. Basically, from our last term of the sum, I want to rewrite the denominator differently. So basically, I want to add and subtract an n times a. So let's see, just from rewriting our limit here. So I want to add and subtract an n times a. So I'll get na plus n times b, then subtract na. So that's just the denominator. So, and now now what I want to do is I'll actually, from our second and third term of our final term, I want to factor out an n. So we get n times a and then plus n times b minus a quantity. Okay, so I'll factor out an n from our second and third term from that denominator. So this will be n and then multiplied by b minus a quantity. And so like I said, just from before, I said that this is, you can see that this is actually a partial sum. So I can rewrite this the input of our limit as a form of a sum. Well, specifically a partial sum, but where we're taking the limit as n approaches infinity. So now what this entails is that we have a partial sum such that the index starts at n equals 0, and then our bound goes all the way up to, well, okay, hold on, let me fix that index. It's we're not going to call it n equals 0, we're actually going to call this r equals 0. So our starting index is r is equal to 0, and then our last index goes from n times b minus a. And then with our 1 divided by n times a plus r. And so what I can do is I can actually divide n from our sum here, and I'll move that outside since this sum does not depend on our n, it depends on r. So when I do that, I'll just move that outside, and I'll get 1 divided by n of our partial sum. So n b minus a, and then r is equal to 0 of, let's see, so this should be 1 and then divided by, this will be a, and then this will be r divided by n. You can actually clearly see that we'll be using the definition of a definite integral to convert this limit. So that's pretty nice. What I can do from here is that I can actually do some substitution. So really, I'll set, as we let x equals r divided by n, okay, so then that would have to mean that, well, suppose x equals r divided by n, I should have said it like that. Then we say that as r approaches 0, then that means, or rather, I should not really approach, but r equals 0, that's the better way to say it. As r is equal to 0, then x is x equals 0, okay? And then as r equals n divided by b minus a, then that means x has to equal b minus a. Okay, and so with that, using the definition of the definite integral, so definition of definite integral, we can convert our limit of the sums into the following integral. So that means, I'll just rewrite the original, so right over here, the limit as n approaches infinity of 1 divided by n of our partial sum n b a, and then r is equal to 0 of, what is it, 1 divided by a plus r divided by n. That's simply just going to equal to the definite integral of our bounds from 0 to b minus a of 1 divided by a plus x. dx. That's not that difficult to show, and because you can see that taking this antiderivative is actually, it's just the natural log. So when we do this, we get that this is just the natural log of a plus x, and then evaluated from our bounds from 0 to b minus a. So then when I do this, we get, let's see, so this will be a plus b minus a, okay? And then subtract that with ln of a plus 0, that's just a, okay? And then we'll just use the rules of natural logs. Well, first let me simplify some things first. So we get ln of a minus a is 0, so we get ln of b, okay? And then subtract that with the natural log of a, and so now we're pretty much done. Using our rules of natural logs, we can combine this into one natural log to get that our limit of our partial sum is actually just equal to ln of b divided by a, like so. This box right here. All right, that's pretty cool if you ask me.